This is Mrs. O'Neill for AP Chemistry, Chapter 20, Section 3, Voltaic Cells. You should have watched the intro lesson on electrochemistry. So here are my notes. He talked about electrochemistry generating current. Well, what does that mean? That means these electrons are moving in a reaction. So he referred to this video that you already watched, but if you do want to watch it, or maybe go back to Chapter 4, Section 4, and just re-look at your notes that you wrote. So electrochemistry, he talked about a lemon battery and the two pieces of metal inside a lemon. So one lemon with one set would cause so much voltage, but if we put many sets together, many lemons with many different pieces of metal and having them all connected, we're going to generate lots of voltage. And this is something that you'll learn in physics, whether you take it now, if you're taking it now, or if you take it next year. You're going to talk about these circuits and how batteries line up and give you a certain voltage depending on what the situation is. Gave you that nice flow as always, flow chart. So here we have an example of a zinc solid piece of metal in a copper +2 solution. And over time, there's going to be a reaction. Well, I don't know about you, but the zinc that's touching the copper 2 solution is no longer zinc in color. That looks more copperish to me. And if you notice, it might be hard depending on your where you're watching it, but this blue solution is very, very dark blue compared to the lighter blue solution here. Well, this should remind you of a single replacement reaction, because really what's happening is the zinc is going into solution and the copper in solution is going now into being a solid. Okay, so this is also called a redox reaction. Why? Because there's reduction going on, there's oxidation going on, and these electrons are flowing. So almost all of your single replacement reactions are going to be redox reactions because, as we said before, when you're starting with an element has a 0 charge on the left as a reactant, and now it's going to be put in a compound on the right as a product, now it has a charge. So there's two elements that are going to be switching places. So one's going from a 0 to a charge, and one's going from a charge to a 0. So it's exactly what I just said, right? So zinc is losing electrons and copper is gaining electrons. The zinc is going from 0 to +2 and the copper is going from +2 to 0. So again, this is the net ionic equation. So the zinc sulfate maybe and copper sulfate maybe. That sulfate ion is your spectator ion. So we talk about two half reactions. This is why we did what we did in the previous sections. So we're going to look at each individual reaction, each individual half reaction. So of course there's going to be an oxidation half reaction and a redox half reaction. Notice where those electrons are, okay? And in a cell, we actually try to separate the two. So again, just looking at that information, now we're going to also look at what's called the reduction potential, and that's how much voltage is going to happen between this exchange of electrons in our zinc and in our copper. So each half reaction is going to have its own reduction potential, which is how many volts that particular metal is going to be able to produce in a reaction. So again, just basically what I said, how much energy is released. So zinc is being oxidized is like a waterfall. So energy up top is coming down that waterfall. So that's why it's usually a positive number. It's positive because that's spontaneous. That's how it would happen. However, if you try to go up the waterfall, right, if zinc would go up and we'd have a negative reduction potential voltage, well, that's not going to happen, right? That doesn't make any sense. That's not going to happen. So negative means it's not going to happen. That's going to be the reverse reaction. But when we have our oxidizing, it's usually in an oxidized way, our reduction potential is going to give us a positive value. So again, copper is gaining and give us that certain voltage. So in a galvanic cell, okay, galvanic cell, nothing's really going to happen unless you complete the cell. Well, how are we going to complete the cell? We need to add what's called a salt bridge, right? So what we just looked at really is just 1/2 of a cell. Okay, so the copper to the zinc, that reaction we just saw, yes, it's a redox reaction, but that's just like one of these beakers. So if we want a galvanic cell, we actually have to let those electrons flow from beaker to beaker, and the only way we can do that is through a salt bridge. So where do these electrons flow? Always, always, always the electrons are going to flow from the anode to the cathode. And I like to say that's in alphabetical order. It's always, always, always the electrons in a galvanic cell is going to flow from the anode to the cathode. So at the anode, the zinc becomes the zinc plus 2, again, losing electrons traveling through the wire to the cathode. So we have, again, our zinc becomes zinc plus 2, and those electrons are going to be moving. So again, at the anode, all of this stuff is occurring. Now at the cathode is where the reduction happens. So again, we're going to be gaining mass over there because the C plus 2 in solution is now going to combine with those electrons and over time become that copper metal. So what's our voltage? How do we calculate that? All we're going to do is add them up. Why are we going to add them up? Well, because we have the electrons from the zinc and we have the electrons from the copper plus 2. We've got all these electrons kind of moving around. So it's going to be that voltage from both of those reactions occurring, right? Both half reactions. So this Nernst equation that he mentioned, way back in the day, you actually used to have to use it. Sometimes even have to formulate it, but at this point it is not on the AP exam. However, he did go through how to understand it. So he talked again about that Le Chatelier's principle, and we need to be able to use again this principle and that Nernst equation and be able to understand what's really just happening in a cell. So again, read over this. You should have already understood this, and hopefully it makes sense through that video and through this notes that I have here. So then he also talked about what's called an electrolytic cell, which is really the opposite of a galvanic cell, but these are the batteries that you guys use, and sometimes these are the rechargeable batteries. So what happens there? So he also talked a little bit about electroplating and what that process is. And he talked about Faraday's laws, and again, back to stoichiometry and what's happening to the changes in the mass. So what happens with electricity deals with mass, and mass also deals with equivalent weight. So he talked about the relationship between electricity and mass. And he had 2 laws to go along with that. So he also gave the example of copper and silver. So if silver has higher mass, it's going to lose more of that mass over time because you're losing those atoms. So on to your packet notes. Your objectives in this section is to consider these voltaic cells producing electricity from spontaneous redox reactions. So we need to know that the solid electrodes, they're going to serve as an oxidation and a reduction part of the process. We're going to list these electrodes where oxidation occurs is the anode, and the electrode where the reduction occurs is the cathode. So pause the video, fill in those blanks, read as you write, and then play to hear my words. So a voltaic cell is also called a galvanic cell. So again, those are 2 words that are interchangeable. It's a device in which these chemical energy is changed to electrical energy. How was that done? Through a redox reaction and transferring of these electrons. So we need to keep in mind again, oxidation is losing, reduction is gaining. Leo the lion goes grr, the box, however you want to figure that out. So pause the video, make sure you're filling in because I believe this is a spontaneous process is in your notes. The salt bridge information is in your notes, and you might have to write down these equations. So make sure that all gets into your notes. And we're going to be also drawing this cell. So you want to draw it to have an example of which way those electrons flow and all of this information. So this is something that you might see on an AP exam. They might actually give you what's called this galvanic cell. They're going to give you something that's occurring here, right? They'll give you the metals, they'll give you maybe the solutions, and maybe you'll have to figure out the voltage. You might have to also figure out half reactions. So keep all of that in mind. You need to know that the anode is always going to have the oxidation occurring at that spot, and the cathode is where the reduction is happening. So this is why it's really, really important to know which side of that half reaction those electrons are going to be on. So the spontaneous reaction is always anode to cathode, like you saw the ABC order. So here's some memory devices, and if you have any of your own, please share them with us. So again, that ABC order, you can read over that. Also, maybe the vowels going together, you might like that. And the consonants going together, you might like that. Oop, I'm sorry, went too fast. And the last one was animals, an ox or red cat. Again, these are things that people have shared with me over the years. So let's take a closer look. Again, I don't make you read too much, especially in your textbook. However, what I am going to ask you to do is pause and read this information. So now, again, you should pause and read this information. Now, the electrons here are going in a little different direction, but you got to be able to know the difference. Again, where are those where's the oxidation occurring? In this case, it's the zinc. How do we know that? Because the electrons are flowing this way, right? So however the electrons are flowing, we know that, again, this is going to be the anode where oxidation occurs, and this is where the cathode is, because that's where reduction is occurring. How do I know that? Because that's the way the electrons are flowing. So this is going to be opposite of how you just drew it, but you need to be able to understand that they can draw it either way. It really doesn't matter which way the beakers are and which way they're showing you those metals. It does, however, show you which way the electrons are going. So again, pause and make sure you understand this information. Please read it. Pause. Please read. Again, I don't ask you to read much. Okay, again, pause and read. So hopefully that made sense. And this is what we call a line notation. So this is just a different way of looking at a battery. Now, I haven't seen this too much lately on an AP exam. However, you might see it written this way in college. So I just want to make sure you're understanding that we have a solid, we have a single line, and that's basically the barrier or the solid inside that aqueous solution. Here's our phase difference or our salt bridge. This is going to be our salt bridge. I'm sorry, the phase difference is here, that single line solid in the aqueous solution, and again, solid in the aqueous solution, and we have that salt bridge. So it just looks exactly like what you just drew and what you saw and what you were reading, but now sometimes they can just give it to you in this kind of notation. So let's ask some questions if they give it to you in this notation. So which electrode does the oxidation occur? Aha, the zinc, because the zinc is going from a 0 to a +2. Again, oxidation box, the charge is getting bigger. So the electrode where the cathode is happening, of course, the lead from the +2 to the 0. So electrons will always flow from which electrode to which electrode. In this case, the zinc, right, is going to flow because that's where the anode is to the cathode. So then what's the oxidizing agent? Would be the lead +2. And write the half reaction for that zinc half cell. Again, we know it's oxidation, so those electrons better be as a product, right? O for oxidation and product on the right side. So again, if we look at something like this, that's what it would look like. That's what we would draw. So here's another visual. So what's happening here is there's going to be, if we connect the metals in this way, those electrons are going to start building up. It's going to stop eventually. Well, why is it going to stop? Because there's going to be too many electrons on this side. There's going to be too much of a buildup. So what needs to occur is that we need the salt bridge in order for that flow of the current. So now, look at that. Isn't that nice? Now the electrons can flow all around and there's not going to be a buildup. So the electricity travels and it completes that circuit. Okay, sometimes they just put a porous disc as well. It doesn't always have to be a salt bridge. It just needs to be something porous for those electrons, again, to have somewhere to flow and to complete and neutralize the reaction. So again, we can also see it this way. That's also a nice visual as far as where the anode is, where the cathode is, and where your agents are. Okay, and another nice flow chart, again, just to give you some more memory devices. Okay, we'll see you in class.